Does it stick to this? Is that steel? I should know it's steel, right? It does not stick to this tube, right? But these guys, of course, stick to each other. So this thing's a magnet, right? Okay. This tube is glass, and it doesn't conduct electricity. This guy conducts electricity, right? These two things are just aluminum pellets. They cannot be magnetized, and of course are not magnetized, right? And if I drop them through there, they just fall through at the same time, right? Like that. If I drop them at the same time, they land at the same time. 1, 2, 3. Yeah? Okay. These guys are magnetized, and if I drop them at the same time, they definitely don't land at the same time. Which one lands first? Glass one lands first, clearly, right? Every time. It's like, right? Now, this is not very convincing. The best one is you take a cow magnet and drop it through a long copper pipe, right? And especially if you cool the copper pipe down with liquid nitrogen, right? It'll take like 30 seconds for that thing to go through there. And the reason that it takes longer for the magnet to go through this pipe is that let's suppose the North Pole is down, right? As it approaches the metal in front of it, current is going to be induced in that metal so that it makes a North Pole that's opposing it, right? And so there's always a North Pole that it's opposing. And as the South Pole on the other end of the magnet goes away from the metal behind it, up above it, the current's flowing the other way, yeah? Making a North Pole above it that it doesn't want to leave, right? So this guy's always being slowed down by magnets, okay? In fact, I tried to make something when I was a kid. I was like in, 4th grade or 5th grade or something, and I read about this, and I tried to make something with magnets and coils of wire that would slow my train down before it like flew off the edge of the setup. Didn't work at all. Okay, it's got to be strong magnets. It's got to be huge conductors, and they got to be really close to each other. Yes, sir.
Are those what they have in like elevators?
Elevators, to slow elevators down? They might. Okay, because here's the coolest thing, right? At PSU, this is the most dramatic example. They use them in roller coasters to slow roller coasters down, right? And I know this because we went and saw at PSU, at NASA, they take 700 pounds and they drop it, and it hits these enormous airbags, right? Okay, that like deflate in the air. There's like these vents where it deflates like that. At PSU, they drop this thing, and it's not a 700-pound thing, but it's probably, I don't know, 500 pounds or something like that, right? And what they have are these little things that stick off to the side that are thick aluminum. They're like 3/4 inch thick, and they're basically these blades. And then down here, they've got these very, very strong magnets right here, right? This thing falls 70-some feet, right? It slams into those magnets, and the magnets never really touch it, right? It just goes shoo, and falls out the bottom. It's the most amazing thing, right? And then I reached in there, right? I reached in there, and I just did a quick calculation. If you turn this potential energy into thermal energy, which is what it's doing, right? Those things should rise about 1 degree Celsius, which you can feel, right? And so I reached in there and touched the things, and I could feel that they felt warmer than the other aluminum. I compared this to this, right? They were like, "Why are you reaching through there and touching it?" Well, it's safe, isn't it? I don't know, right?
Drop tower broke.
Their drop tower broke?
Yeah.
How do you know?
Because I know the guy who works on it.
Oh.
Matthias guy.
Oh, yeah. And they broke it?
Yeah, they crashed it somehow. It was on the top floor, and the braking system failed, and it crashed all the way to the ground.
Oh.
It was pretty bad.
That's sad. That's sad news because, well, it's good news that they have it because once it's up and running, it's like that's a lot closer than Cleveland.
Yeah.
And it's just as good as Cleveland's. But anyway, that's just extremely dramatic. I have other demonstrations. Okay. This is kind of funny. This is a hard drive magnet. Okay. This is a bar of aluminum. These magnets do not stick to the aluminum. Okay. Watch this. This is funny. That's kind of cool, isn't it? Watch. Isn't that falling unlikely slowly? Isn't it? Isn't that weird? Watch it speed up once it leaves the poles of the magnet. Oops, here goes it. Okay. You can also take this and just slide it. I'll pass it around. You can feel it. If you just sort of bow that thing, right? You can feel the resistance. It's not the friction force, it's a magnetic force. I'll pass that around. You can feel that. And then this is the most dramatic thing, I think. Okay? We'll use Jordan Raffo's binder because he gives it to us so freely. Okay? Watch this red cart. Voila. Down it goes. Yeah? Can we see that in the camera? We can't see that with the camera. The camera's not pointed at it. There we go. Okay. Watch it go. This is the normal behavior of an air track cart is that it speeds up, yes? Okay. What's wrong with this air track cart? That's kind of interesting, isn't it? Why is it going so slow? Here. Holy cow. Now, this track is aluminum. The magnets cannot stick to this track. This glider is aluminum. They can't stick to that glider, right? Yet it's being slowed down, right? Well, why is that? Well, because it's really, really, really strong magnets. They're pointed toward the track, right? And so what it's doing is, let's suppose, and really what it is that each magnet has a north side and a south side, but let's just make it simple. Let's suppose that there's a north pole magnet facing into the track. Okay? In front of the cart, as it approaches, there's a north pole magnet. The eddy currents are all going anti-clockwise, like this, right? And opposing the motion. Behind it, as the north pole goes away, the eddy currents are going clockwise and making a south pole magnet that it doesn't want to leave behind. Isn't that marvelous? And you can even take it and push it. And it immediately damps down. It's like on a car? Yeah, in fact, the Toyota Prius does this, right? Of course, it's doing it with a motor, right? That's reacting like a generator, but it's the same thing. It's inductive braking, right? But you could do it with really strong magnets. I think the reason that they don't, maybe, is that the magnets, you'd have to have really strong magnets as they get jarred or bumped, right? And then, of course, it would have no holding power at zero velocity.
Yeah, but I mean, it'd be a great addition.
Yeah. Yeah, have that so you don't break, like as you go down a hill. And then the final thing, I'll give you this one. Okay. Take a look at this. Take a look at this. Okay. If you look in this side of this, these things damp down pretty fast. If you look at this side here, okay, and there we go. Okay. If you look at this side, this looks like a big piece of aluminum right there, doesn't it? Doesn't it? Yep. And if you look inside there, it looks like there's a couple magnetic poles right there, really close to the aluminum. What do you suppose they're doing? Slowing it down. So as it sits there and swings back and forth, it's getting it's inducing eddy currents. These are always resistive forces. And then the beauty of that is that it has zero force when the velocity is zero, right? The EMF, when V is zero, the EMF is zero, right? And so it doesn't sit there and tip it either way. If you did a frictive force, that is, if it touched something, it could deflect up and stop just randomly above or below, right? So you could do that. You can also do it with like a viscosity, with like oil, but this is much cleaner and nicer, right? So that's kind of cool. Isn't that cool? I think that's cool, right? And then, of course, the uber thing, the uber eddy current is the Meissner effect. Okay, so let's see if we can pull up that video. Let's see if it's still on there. Let's see if this lets me click on a link. YouTube, amazing physics. Okay, so here is the deal with the Meissner effect. If we've got a superconductor, okay, if we've got a superconductor, we put a magnet here, and let's just put the magnet with the north side down, okay, and the south side up like that, just to make it simple, but it doesn't matter, okay, and we put this thing here. There's going to be a eddy current that goes this way on the superconductor, yes? And this board or the aluminum or whatever that they have, okay, the currents die